Under compounds of alkaline earth metals, let's first talk about oxides and hydroxides of alkaline earth metals. They form oxides of the type MO, 1:1 oxide, and hydroxides of the type MOH taken twice. They form oxides of the type MO and hydroxides of the type MOH taken twice. Beryllium oxide and beryllium hydroxide, these are amphoteric. Beryllium oxide and beryllium hydroxide, these are amphoteric substances. Others means oxides of magnesium, calcium, strontium and barium. Even their hydroxides are basic. Others are basic. And basic strength increases down the group. Basic strength increases down the group. So the least basic among them is magnesium oxide, whereas beryllium oxide is amphoteric. Now let's see amphoteric substance is one which can combine with both acids as well as bases to form salts. Let's see how beryllium hydroxide reacts with acids and bases. Beryllium hydroxide, if you make it react with sodium hydroxide, as I told you, this is amphoteric. It is expected to react with both acids as well as bases. Sodium hydroxide is a base. So when they react, you get Na2BeOH taken 4 times. This is sodium berylate. It's a complex compound. In a similar manner, you can expect beryllium hydroxide to react with HCl. This is a solution phase reaction. You are actually supposed to get beryllium chloride, but in solution it exists as BeOH taken 4 times 2 plus Cl2, that is 2 minus. So this is the substance which is formed presence of acid, and in presence of base you get berylate. That's how the reaction takes place. So these two reactions demonstrate amphoteric nature of beryllium hydroxide. A similar reaction you can expect for beryllium oxide also. Beryllium oxide gives sodium berylate, and with HCl you get beryllium chloride. That's about oxides and hydroxides of these substances. Let me tell you one more thing. As you go down the group, thermal stability of hydroxides increases down the group. That's all about oxides. Let's move on to the next class of compounds of alkaline earth metals. Then the next class of compounds we are going to learn are halides of 2A group. Halides are binary compounds of alkaline earth metals with halogens. So this is the general formula of an alkaline earth metal halide, MX2. Here remember, beryllium halides are covalent. Because of their covalent nature, the covalent nature arises due to high polarizing power of Be2+, and because of their covalent nature, they exist as molecules and they are electron deficient molecules. Others are ionic. Halides of other elements are predominantly ionic. Now, BX2, they exist as polymers. It is a consequence of electron deficiency of these substances. Look at the case of beryllium chloride. See, beryllium chloride exists like this. This is a molecule of beryllium chloride. The central atom beryllium is surrounded by only 2 bond pairs. It has got only 4 electrons in its valence shell, so it is highly electron deficient. To overcome this, it will go for polymerization. Look at the way they undergo polymerization. The lone pair on this chlorine will be donated to the vacant orbital of this beryllium, and the lone pair of this chlorine will be donated to this. In a similar manner, it continues. it continues here. So in this way, you get a polymeric structure in which each beryllium will be surrounded by 4 bonds. Out of these 4 bonds, two are ordinary covalent bonds, and the other 2 are dative bonds, which are formed due to donation of lone pair of chlorine to the vacant orbital of beryllium. These are polymeric. So under ordinary conditions, beryllium chloride does not exist as discrete molecules. It exists as a polymeric structure of this type. This is under ordinary conditions. Same beryllium chloride will become dimeric. This is a dimer of beryllium chloride. Look at this. This is a polymer. This is a dimer. This exists in the vapor state. In the vapor state, it exists as a dimer, which looks like this. Here, you can have dative bonds of this type. This is a dimer of beryllium chloride. It exists in vapor state. In the solid state, it is a polymeric species. Same beryllium chloride exists as a monomer like this, a linear molecule with bond angle 180 degrees, sp hybridization of beryllium. This is possible above 1200 Kelvin. Above 1200 Kelvin, it exists as a monomer. In the vapor state, it exists as a dimer below 1200 Kelvin, and when it is in the solid state, it exists as a polymer of this type. In the polymer, it is surrounded by 4 bonds. In the dimer, it is surrounded by 3 bonds, and in the monomer, it is highly electron deficient, and it exists under drastic conditions, that is at a temperature above 1200 Kelvin. There are some more points regarding halides of these elements I'll discuss after some time. Just go through this once again. Beryllium halides are predominantly covalent, others are predominantly ionic, and because of covalent nature, they are electron deficient, and they try to solve the problem in this manner. Another important feature of these halides is these halides exist as hydrates. It is because of high heat of hydration of alkali metal ions. Because alkali metal ions are dye-positive, their charge density is very high when compared to alkali metal ions. Alkaline earth metal ions have very high heat of hydration. Their salts preferably exist as hydrates. So, magnesium chloride exists as MgCl2.8H2O. Calcium chloride. Similarly, strontium chloride, 6H2O. Barium chloride, 2H2O. You can realize barium is taking only 2 water molecules of crystallization. The reason is hydration energy of Ba2 plus we have seen is minimum, so its ability to take up water of crystallization is relatively less. Another point of importance is these substances on heating lose water and they give rise to anhydrous MCl2. This is very simple. They on heating they lose water of crystallization and give rise to anhydrous substance. This is anhydrous salt. Whereas if you heat magnesium chloride, you end up with magnesium oxide. That means magnesium chloride hydrate, when it is heated, it will undergo hydrolysis and you get magnesium oxide. If you want anhydrous magnesium chloride, you need to heat it in presence of HCl gas. In this way, you can get anhydrous magnesium chloride. So, halides, hydrated halides of alkaline earth metals, calcium, strontium and barium can be dehydrated by direct heating, whereas for magnesium halides, it is important that the corresponding hydrogen halide gas has to be circulated while heating to get anhydrous salt, otherwise hydrolysis takes place. That's about halides of alkaline earth metals. The next class of compounds of alkaline earth metals are carbonates. We are going to discuss about their carbonates. The general formula of their carbonates is MCO3. So you have beryllium carbonate, BeCO3, magnesium carbonate, MgCO3 and so on. This is the general formula of carbonates of alkaline earth metals. These carbonates, when they are heated, they lose carbon dioxide and become metal oxide. For instance, if you are heating calcium carbonate, this decomposition of calcium carbonate is reversible. You get calcium oxide and carbon dioxide. See, what makes it reversible is the complementary nature of these substances, in that calcium oxide is a basic oxide while carbon dioxide is an acidic oxide. These two have complementary nature, so they can react once again to give rise to calcium carbonate. If you want to avoid this process, you can exploit this. This is a solid, this is a solid, and this is a gas. So if you allow carbon dioxide to escape out, then it will not be available for backward reaction to take place. So this reaction can be made to proceed more in the forward direction by allowing carbon dioxide to escape out. There are two things which are very, very important. One point is regarding thermal stability. Thermal stability increases down the group. Thermal stability of these carbonates increases down the group. I'll tell you the reason. The reason is carbonate is a large anion, and to stabilize a large anion, you require a large cation. So as you go down the group, the size of the cation increases and its ability to stabilize the carbonate and increases. That's the reason why stability increases down the group. Solubility decreases down the group. Regarding thermal stability, I would like to add one more point. Beryllium carbonate is so highly unstable that you can store only in presence of carbon dioxide. Beryllium carbonate can be stored only in presence of carbon dioxide environment. Now coming back to solubility, the only soluble carbonate among alkaline earth metal carbonates is beryllium carbonate, others are insoluble. So solubility decreases down the group. Most insoluble among them is barium carbonate. And the soluble carbonate, there's only one soluble carbonate actually, it is beryllium carbonate. So that is about carbonates of alkaline earth metals.